As we were brainstorming project ideas, we knew we wanted to combine artificial intelligence and robotics to create a fun, interactive game for all to enjoy. We decided to make a rock, paper, scissors robot that competes against a human opponent. Our system has 3 key goals: to detect a user's move using computer vision, respond with an appropriate move using a robotic hand, and provide user feedback by displaying the game outcome on a graphical interface. This is a demonstration of a user playing against our autonomous robotic system. Our design has 4 main components. First, we use the NVIDIA Jetson Nano, which is a single-board computer equipped with a GPU. We chose the Jetson Nano as our single-board computer in hopes of using its GPU for AI inference. We chose a Raspberry Pi Pico microcontroller for signaling the robotic hand's servo motors. The Pico receives commands from the Jetson Nano and generates the appropriate PWM signals to achieve the desired position. Next, our robotic hand was made using 3D printed parts and tension strings for a realistic look and movements. Finally, we used a webcam to capture live video feed of the user's hand, which was sent via USB to the Jetson Nano for processing.
For our hardware requirements, we had to construct a robotic hand consisting of 5 fingers, including a thumb, and have complete robotic hand movement programming with finger joints that are able to rotate a minimum of 67.5 degrees each synchronously and to be able to show various game symbols that are reasonably identifiable by the user. In order to meet our hardware requirements, we broke our development cycle up into 3 major milestones, the first of which being the development of a prototype finger that opens and closes like a realistic finger would. In order to do this, we utilized rubber bands and fishing lines that would mimic the functionality of muscles and tendons. Some of the challenges that we faced along the way was having enough degrees of rotation to be able to properly mimic human motion, having the finger snap back properly to an outstretched position. Overall, the design worked well and we were able to move forward with some minor adjustments. For milestone 2, we had to develop a prototype hand that was able to open and close as a realistic hand would within a hand's typical template. The challenges that we faced in doing this was the organization of the servos so that they fit within the footprint of a typical hand, and also the combination of finger tensioning and servo strength and playing against each other to make it look realistic. Overall, this prototype was bulky and had issues with tensioning and was tedious for us to build and rebuild, so moving forward we decided to move with existing hardware that had been already developed. Milestone 3 was the construction of our final robotic hand. In order to do this, we found an existing model, that way it was more aesthetically pleasing and worked more efficiently than the design we had built. Some of the challenges that we faced in doing this was adapting the chosen model to our materials and needs that we had currently available. The way the hand functioned is by using 4 servos that are tied to strings that will then pull tension onto the fingers, opening and closing them in a realistic motion. And then there is a micro servo implanted within the hand that will rotate the thumb, leading towards more realistic action. Overall, this met all our design specifications, and the only issues we faced were minor cosmetic issues.
For our AI model, we wanted something that could generalize well to real-life data, recognizing gestures regardless of position or angle in the video frame. Our AI model is built on top of Google's MediaPipe framework, which provides a hand detection computer vision model. The MediaPipe model plots 21 coordinates to mark landmarks on a detected hand. Each coordinate is plotted with X, Y, and Z coordinates, giving us a vector with 63 features for each hand capture. We use these coordinates as input data to our machine learning models, and have created our own dataset containing over 4,000 coordinate vectors for the rock, paper, and scissors gestures. We started by implementing a few basic supervised learning models using the scikit-learn Python library. We tried decision tree, logistic regression, k-nearest neighbors, and random forest models. Our best performing model was a random forest ensemble learning model, which uses a forest of 50 decision trees to make a prediction of the hand's gesture based on the coordinate vector it's given. In our implementation, the trees have no max depth and look at a maximum of 7 features for each split. This random forest performed perfectly on the test split and tenfold cross-validation, but generalized poorly during in-the-field testing on a live video feed. Our final AI model is a deep neural network implemented using the PyTorch Python library. Our model is fairly simple, having only one hidden layer between the input and output layers. Between each layer, we use ReLU as our activation function and employ dropout with a 30% probability to help with generalization. We use the atom optimizer with momentum, L2 regularization, and a cosine annealing learning rate scheduler. We trained for 300 epochs and performed tenfold cross-validation to thoroughly capture the model architecture's robustness. We take softmax on the output tensor to determine the rock, paper, scissors probability distribution. We also take inspiration from the data augmentation techniques used in convolutional neural networks to apply our own augmentations to the plotted hand coordinates in the data training set. Training with augmented training data helps to improve model generalization, as the data has new random augmentations during each training epoch. Here you can see examples of hand coordinate vectors being transformed by random flips, rotations, scalings, and translations. These transformations are all applied with random probabilities and randomized values to the data in the training loop of our model. Here, you can see the loss curves from the training and validation of the neural network during cross-validation. We saved our best-performing model from cross-validation, which had a final cross-entropy loss of 0.0620 and an accuracy of 0.9923 on the validation split of the dataset.
The structure of our software consists of 3 layers. The graphical user interface, which is a widget-based tkinter application with callback functions to execute parts of the game. A game logic/AI layer, which uses programming logic and predictions from the AI model to control the flow of the game. And motor control via the MP remote tool, which calls routines on the Pico to activate the servos. The user interface is designed to be sleek, aesthetic, and minimalist. It contains start and stop buttons, a user feedback area, and the camera view, so the user knows that their hand is in view of the system. We went with a dark theme to match the color of the 3D printed hand. When the start button is pressed, the screen will show a countdown, 3, 2, 1, and at the end it will display the winner of the match, as well as the choices that were made by the computer and the user. This flowchart shows the process executed in a single game. After the program is running, and the GUI widgets, camera, Pico, and neural network are all initialized, the program will wait for the user to click the start button. Once it's clicked, the game logic will generate a random move, either rock, paper, or scissors, and prompt the user to make their move by initializing the 3, 2, 1 countdown. When the countdown finishes, the program will send a signal to the Pico, which will call the routine to move the hand to the computer's choice. And the AI model will make a prediction based on the user's hand in the current frame from the camera. After the prediction, the program will determine the winner or if the game is a draw. An error message will be printed if the user's hand is not in the frame. Lastly, the final results are displayed on the GUI, the hand is reset, and now the system is ready to play a new game. That concludes the technical overview of our rock, paper, scissors opponent project. This project was a successful combination of artificial intelligence and robotics. We had to integrate many pieces, including servos, a 3D printed hand model, a microcontroller, the NVIDIA Jetson, a neural network, and a graphical user interface to achieve a working final project. Fortunately, our project progressed in a timely manner, met the design requirements we set in our project management plan, and stayed within financial constraints. We hope you enjoyed this project outline video.